Right, we're going to look at Kirchhoff's laws. Kirchhoff's laws. Now in electronics, if you've got a nice little simple circuit, maybe like this, with a battery and a resistor, you could, if I gave you the values of the battery and maybe the current, you could easily find out everything you needed to know about that circuit using Ohm's law and how resistances work in series and parallel circuits. However, if you're given a very difficult circuit or a more complicated circuit, so maybe it's like this, and there's another battery in here, another resistor in here, or maybe there's another resistor up. Let's say it joins there, another resistor here, something like that. A bit harder to do. So the giveaway is if you see two batteries in a circuit, you should go ahead and start using Kirchhoff's laws. So what are Kirchhoff's laws? Well, there's two of them. The first one is the current law, Kirchhoff's current law. And Kirchhoff's current law, in fact both the laws are really easy just by themselves. The current law says that the current into a junction, so the current in to a junction is equal to the current out of the junction. And what do I mean by that? Well, a junction is like this point here. That's a junction where there's wires meet each other. So say I was to zoom in on that and draw it again. I might draw it over here. That's the junction there, and maybe there's a current going in here, I1, and a current coming out, I2, and another current coming out, I3. So the current law just says that the current in has to be the current out. You can't just invent current from nowhere. So in this case, I1 gets turned into I2 and I3. It's a pretty simple law by itself. You might say, well, what happens though if we get the value? Say that I1, someone now tells us, oh yeah, I1 is 0.2 of an amp, and I2 is 0.3 of an amp. So we've got 0.2 coming in, and that turns into 0.3 here. How is that possible? How can you get more current? Well, if we put the numbers into our law we've got here, we've got I1 equals I2 plus I3. We've got 0.2 equals 0.3 plus I3. And if you solve that, you get minus 0.3 on both sides. You get minus 0.1 equals I3. So I3 is minus 0.1. What does that mean? It means that I3 is actually going in this direction here. So I1 comes in and I3 comes in and I2 comes out. The point I'm trying to make is, with the current law, as long as you write down any sort of rule that makes sense, I1 equals I2 plus I3, if you get the directions wrong, it doesn't matter. When you put the values in, the directions will come out of the formula, and it will all work out in the end. Okay, so that's the current law. That's the first one. Let's go. Maybe we'll go blue. Is that blue? Yep. For the second one, the second one is the voltage law. And the voltage law says that the voltage around a loop equals 0. So best to go through and do an example of this. Let's say I have just the simple circuit up here. We don't need to use Kirchhoff's law for this, but Kirchhoff's law still works for this. That's the point. We'll end up using Kirchhoff's law for something hard like this, but for now we're just going to draw this simple one here. Now let's say I have 6 volts and the current's going this way and it's 0.1 amps, and we've got to find R. So let's go through and do our voltage law. The current around a loop. What that means is you have to go around this loop. So I pretend I am a little man walking. So I'm going to be walking this way. I'm going to start at that point and I'm going to walk around the loop, and I'm going to walk around. I'm going to draw a circle around here. That's the way I'm going to go. So I'm walking along, walk, 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 walk. I get to the battery. I go through a battery, and that's a voltage rise. Okay, that's a rise, and it's a rise of 6 volts. I walk, 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 and I go through my resistor. That's using up voltage, so that's a voltage drop. And so because it's a drop, it's a minus. I don't know what voltage it's being dropped by, but what I do know is Ohm's law, V equals IR. So the voltage that this loses is actually just the current that goes through it times its resistance. So 0.1 is its current, 0.1 times R, which I don't know. Then I walk, all the way back to where I started from, and I've gone through no other components. So therefore, I'm back at the start, the voltage around the loop equals 0, that equals 0. And now I can solve that. So 6 minus 0.1 R equals 0, 6 equals 0.1 R, R equals 60 ohms. Now I'm going to solve it again, but I'm going to walk around the loop in another direction. So let's do this with another colour. Let's do it with red. I'm now going to start from, I'll start from the same place. Why not just start from the same place? But I'm going to go around this way. So now my man, he is walking that way. So let's go. I walk. Now I get to the resistor. I'm doing it this way because this is where you come across a little bit of complication. The point is, well, there's two, is that if you go through a battery the correct way, so if you go through a battery, you go in through the negative and out through the positive, like current likes to do. If you're walking around the loop and you do that, then it's a voltage rise. It's plus in your equation. If you walk through the battery the other way, it's going to be negative for your equation. So you're going to see that when we walk through, because we're going to walk through that battery backwards. The other one is, so this is example one, you're going through batteries. The other one is you're going through resistors. If you go through a resistor and you go the same way as the current, okay, if you go that way, the same way as the current, it's a negative voltage. It's a voltage drop. However, if you walk through against the current through a resistor, it's the opposite. It's plus V. So let's do it for this equation here. This man's walking, he's walking. He's going through a resistor in this direction, but the current is coming from the other direction. So as we set up, and we're doing this equation again, but we're doing it for the other direction, we see that the first, well, it's going to be negative, it's going to be positive because we're going through against the current. What voltage is it across there? We don't know. We've got to use IR, so I is the same, 0.1 times R. Then I'm walking, and now I'm going through the battery the opposite way than what you'd normally go through a battery. I'm going into the positive first and out through the negative. So that becomes negative. And what is it? It's 6. And that equals 0. So then I rearrange this. I get 0.1 R equals 6. And I've got exactly the same equation. I get the same thing. I did that, and you might be a little confused at that, but I did that to show it doesn't matter which way around a loop you go as long as you follow the rules. And the second thing I wanted to show you was, if you go through a battery forwards, it's positive volts, like here. If you go through a battery negative, it's negative volts, like here. And the same with a resistor. If you go through a resistor the same direction as the current, it's negative. If you go through a resistor the opposite direction of a current, it's positive. And that's going to help you out when you do a harder example like this one here. We've got multiple loops and we've got batteries everywhere. So eventually you are going to go through a battery backwards. And that'll help you out for that. Okay, but those are the two of Kirchhoff's laws. We've got its current law here, and we've got the voltage law here. By themselves, they're not particularly hard. Okay, we're going to do a harder example in the next video to show you how it can work in a hard example. All right, where do I get out of this?